who's from the Hebrew University in Jerusalem, on central limit theorems for linear statistics for biorthogonal ensembles. So the motivation for this work is that we wanted to understand central limit theorems for orthogonal polynomial ensembles from a general perspective. As you may know, orthogonal polynomial ensembles is that constitutes a class, a very general class of determinantal point processes that have many important examples. For example, the unitary ensembles is an example that we saw yesterday quite a lot. And, but also, if you take discrete orthogonality, you come in the area of tilings, of planar domains, and okay. So, but typically these models have been studied a little bit separately. Central limit theorems have been found in both cases. So yesterday we saw a theorem by Johansen on central limit theorems for unitary ensembles. I will repeat this briefly. But we also have central limit theorems in tiling models and connections to fluctuations in connection with the Gaussian free field. But usually the proofs are separate. And we wanted to understand these central limit theorems from a more general point of view. If you start with an orthogonal polynomial ensemble with a general measure, is there a general principle that leads to this central limit theorems? And the answer to that is yes, and I want to discuss that today. And in particular, our approach is quite nice in general, in the sense that we have a central limit theorem with very low regularity on the measure mu that generates it. Okay, and then we realized also that since our proof is quite algebraic, we can extend everything to biorthogonal ensembles as long as there is some kind of recursion for the generating family for the biorthogonal ensembles. So let me start out briefly with some notation. Suppose we are given a random collection of points x1 to xn, and then we can test this random configuration with a function f, which gives a linear statistic, which is the random variable that just sums the value of f in the random points. Okay, so in this talk, I'll be interested in the asymptotic behavior, of course, as n goes to infinity, and I will always assume that x1 to xn are coming from a biorthogonal ensemble, which also means that we are in the beta equals 2 case. So for those of you who like general beta, I apologize. But I hope I can make up for it with proving some strong results. Second, I will always assume that my function f is a C1 function with at most polynomial growth at plus or minus infinity. And I'll say a few words about it in the next slide. So typically, if you want to study asymptotics for these linear statistics, the first step comes from the limiting distribution nu of the points. So suppose that like in the unitary ensembles, we have a limiting distribution, then that means that 1 over n times the linear statistic converges to the integral of f against the limiting density. And once you're in that situation, it's natural to ask, what about the fluctuations of this system when n goes to infinity? And in several important examples, and I will show you 2 of them before I go to the models I want to discuss. You have a following central limit theorem that xn, if you center the linear statistic, it converges without normalization to a normally distributed random variable. Okay, for some sigma f squared as n goes to infinity. So the important point that you need to know here is that there is no normalization of the linear statistic. If you compare it to IID random variables, you typically have to normalize by a square root of n to get a normally distributed random variable. But here we don't normalize.
That's because we have used a smooth function.
Exactly, that's maybe the next. So because we use a smooth function, because in particular this means that the variance remains finite. If you have a function with a jump discontinuity, then the variance typically grows. And then there are principles by Koster-Leibowitz and Soshnikov who proved that you also have a central limit theorem in that case. But then you need to divide by the variance. But if you have a smooth statistic, this is a kind of sensitive central limit theorem, because each term, note that this xn is a sum. So in each term in the sum is of the same order as magnitude as the total fluctuations. So this makes this a very sensitive theorem. Okay, so I want to give one example. First example is the unitary ensembles that were discussed yesterday. Suppose we have eigenvalues of a unitary ensemble. So we have the van der Monde squared and this exponential with the confining potential. Then as n goes to infinity, as I think most of people know here, is that there is a limiting distribution for the random points x1 to xn that can be characterized in terms of the minimizer, unique minimizer of an energy functional. That is written here. Okay, but we are interested in the fluctuations, and then I want to recall this theorem by Johansen. It was also discussed yesterday under certain assumptions on V. In particular, these assumptions are such that we have that the limiting distributions of points accumulate on a single interval. So we are in a one-cut case. This is very important. Then we have a linear. Then we have a central limit theorem that says that the centered linear statistic converges to the normally distributed random variable with a variance given by a sum of this half Sobolev norm, where these coefficients are actually expressed in terms of f, where we see the endpoints of the interval actually appearing in this integral. So this is the length of the interval, half the length of the interval, and here we have the midpoint of the interval. Okay, so some history about this theorem. So for polynomial V, a one-cut case, and for some sufficiently smooth, so f is h2 plus epsilon. This has been proved by Johansson in '98, and later this was extended by Schabrina and Kirchebauer and Borot-Guillaunet recently also to allow real analytic V. And okay, so and actually also there has been a complete expansion of the linear statistic if you also your test function is analytic. So the one-cut case is essential here in this theorem. And in the multi-cut case, it has already been proved by Pasteur in 2006 that there's not necessarily a Gaussian limit for this case, for this linear statistics. Okay, but there has been recently some very nice works by Schabrina and Borot-Guillaunet where the partition function was, where there was a full asymptotic expansion of the partition function, which also characterizes the fluctuations in the multi-cut case. And I should say that everything for the proofs of this theorem rely on the loop equations that were explained also yesterday. And they hold for general beta, but I will only consider the beta equals 2 case in this case. Okay, so, but you can also do this for other classical, this was for the unitary ensembles. You can also do this for the other classical ensembles, and there are some recent works also there. So the second example that I want to discuss is about tilings of planar domains. Just an example, quick example for the lozenge tilings of hexagons. So suppose we have a ABC hexagon which is placed on the triangular letters. So the corners on the triangular letters. We're going to fill this hexagon with lozenges of the following type. So we have the green one here pointing right down, and then the blue one pointing left down, and then this diamond here. And we're going to tile this hexagon with these tiles. For example, in this way. Okay, so this is one way of tiling this hexagon. Of course, there are many different ones. And so there is a natural way of defining a probability measure on these tilings, but just take uniform measure on all possible tilings. Okay, so this gives you a probability measure on all possible tilings, and we ask, of course, the question: what happens when the hexagon is very large, or that the mesh of the lattice is very small? Oh, sorry, I pushed the wrong button here. So here I stole a picture from the internet. I apologize if the creator is in the audience. We have a reasonably large hexagon that we have tiled in this way. And what you typically see is that there are some corners here. In the corners, we only see one particular type of tile. So these are the frozen regions in the hexagon. And in the middle, there is a disordered regime. Okay? And these kind of models have been studied a lot recently. And I don't want to go into detail. I just want to mention some words. If you want to analyze these tilings, then one way of doing that is one naturally associates a height function for these tilings for which the graph is a stepped surface, and for the context in this course, for this lecture, the pairing of this random height function actually is a linear statistic. Now, if the to study these, when the size of the hexagon grows large, you typically have a limit for your height function, and then you ask about the fluctuations around this height function, and the fluctuations are typically described by the Gaussian free field if you are in the right coordinates. I don't want to specify the precise structure here, but I just want to mention this result, and there's a lot of results in the last few years around this theme. I don't want to explain it, the precise result. I just want to mention, to go to the one-dimensional fluctuation. So I should actually first say that this hexagon tiling has been done recently in a paper by Petrov, where he proved the Gaussian free field fluctuations in the tiling model. But we will actually be interested in the purpose of this talk that we are always in one dimension. So what I will do is I will take my tiling of my hexagon, and I'll cut it somewhere by a vertical line, and I'm gonna draw the dots where the centers are of the red tiles. Okay, and these are my points, and these forms my point processes. So, and actually you can prove then, this was proved in 2002 by Johansson, that the probability distribution on these centers is given by a van der Monde squared times the Hahn weight. Yes, this is the same Hahn for the last talk. Yeah. Yes, yes. Yeah. So yeah, he actually, I looked him up because of the last talk, and apparently he died in '98. So, yeah. Okay, so and then what you can prove is that if you look at linear statistic for these 4 points that are chosen randomly along this weight, that there is a central limit theorem, which is a one-dimensional section of the Gaussian free field in a complex structure. Okay, I don't want to specify precisely what this variance is here. I will do that in a minute anyway. Okay, but these are 2 results that are typically proved in different methods, and I want to show you later that these follow from a more general central limit theorem that I will show you. I will discuss, and actually the proof for it is not so difficult. I hope I have time to prove it actually. Okay, so this brings me to my first class of examples that I want to discuss. These are the orthogonal polynomial ensembles. So both these include both examples that I gave before. So let mu be a Borel measure on the real line with finite moments. Then I can define the orthogonal polynomial ensemble of size n as just the van der Monde as the probability measure on Rn, consisting of the van der Monde determinant squared times the product of the measures. Here. Okay, and I will allow the measure mu to also depend on n to include unitary ensembles. We typically have varying measures, so I will allow this measure mu to depend on n. But both varying and non-varying will be discussed. Okay, and then we ask what are the minimal conditions on the measure mu such that we have a central limit theorem. Can we do this more generally? Okay, so first of all, these are orthogonal polynomial ensembles. Why are they called like that? I will have to introduce some notation. Well, given the measure mu with finite moments, I can give define the orthogonal polynomials, which I will denote by pk of n. So pk of n is a polynomial of degree k, which is orthogonal to all the other polynomials with respect to this measure mu. Okay, so I have 2 indices. The first k is for the degree, and n I have a second index because I allow my measure to vary. Now, if you have orthogonal polynomials, of course, we know that there is a recurrence coefficients, which also discussed by Balint yesterday. And actually, I apologize because you use a different convention. I used the a's in front. You had the b's, I think. So, okay, that doesn't matter. But so to me, the a's are in front and outside, and these are the ones that are positive. And the bk's are on the diagonal. Okay, and then you can organize these recurrence in terms of a Jacoby operator around here. Okay, and we will use the recurrence and the Jacoby operator a lot for our central limit theorem. Okay, so the next thing that one needs to introduce is the reproducing kernel, which is just the sum of the product of the two polynomials in the degree in the variable x and the variable y, and the sum goes from 0 to n minus 1. Okay, so just for future references, this satisfies a reproducing property. It's easily checked and well known that if you integrate out, if you take the product of two of those kernels and you integrate out one of the variables y, then you get kn back again. So in other words, kn is an operator. It's an orthogonal projection. So kn star is kn, it's symmetric, and kn squared is kn, and it has rank n. I mentioned this for a purpose. And of course, we also know that for orthogonal polynomials, there is, instead of computing the sum, you can actually get a nice expression in terms of the Christoffel-Darboux formula. The kernel can also be written as a difference of two products of polynomials divided by x minus y, where you also see the recurrence coefficient appearing here. Okay, well, we'll use this formula in a minute. Okay, and then there's the well-known statement that the orthogonal polynomial of size n, associated with a Borel measure mu, is a determinantal point process on R, with the kernel kn, where you have the kernel kn is the Christoffel-Darboux kernel, right, with reference measure mu. Now, we all know what this means, but just for our linear statistic, which is the object we want to study, I just wanted to mention that the moment generating function for the linear statistic is actually given in terms of a Fredholm determinant. Okay, and that's the starting point of the analysis later. Okay. Okay, so the first question that, okay, we're interested in trying to find the, so we are interested in.
So in that formula,
yeah.
You're not using anything about regularity.
No, this is just general for, it's general for determinantal point processes. Right? So the question about regularity comes here. Okay, so we are asking for a central limit theorem, but is it even clear a priori if you have a general measure mu? Maybe you can cook up some crazy example that we actually even have the right size of the fluctuations, right? So not even so why don't we have to normalize at all if for a general measure? You may expect that if you can cook up a crazy measure where you actually have larger fluctuations. Okay, so first that brings me to a first theorem that we prove. And that's the following. So you can prove that the moment generating function for the centered fluctuation is actually bounded by a exponential of a times t squared times the variance, where a is some universal constant. It's very explicit. It's large in our paper, but it doesn't matter. It's like 10 to the 10. It doesn't depend on any of the parameters in the problem. Okay, and t is a complex parameter, can be complex, and it's very small. Okay, it has to be smaller than 1/3 times the bound norm of f. Okay, but I don't need any assumption on f other than the fact that it's bounded. That's important. Okay, and from this inequality, you can easily prove that there is a concentration inequality, that the probability that the fluctuations deviate more than epsilon actually are smaller or equal than 2 times the exponential of minus the minimum of these two numbers. When the first number you see the variance appearing, and the second one is just this subnorm of f. Okay? It doesn't depend on anything. No, just it's really like 10 to the 10. Yeah. It's a little bit large in our paper, but yeah. Actually, I wanted to say, I mean, yeah. So we compute this in the paper. It's a sum, and it's a very large number, and it's by no means optimal. This is not an optimal. We just give it's very large, but it's fixed. It's really a number. It doesn't depend on any of the parameters. Okay, so and I want to say actually that. Okay, we only use this now in the fact for orthogonal polynomial ensembles, but this holds for any determinantal point process with a kernel Kn that satisfies these properties. Okay, you can prove that if you have if you have an operator that is an orthogonal projection, then there is a determinantal point process with that kernel, and that's sufficient actually for these two conditions, sufficient for this concentration inequality. Okay, and it's important also to note it's also general in that sense, but it's also for any bounded function f. Okay, typically concentration inequalities come with some regularity in the measure or in the function, but here we have little. Okay, but to make this into a useful concentration inequality, we need, of course, still to estimate the variance here. Right? So everything we estimate everything on the variance. So first of all, I want to say that there is always a crude bound on the variance. The variance can always be bounded by the subnorm of f times the number of points in the determinable point process, which is n here. Right? So that's a simple bound that you can prove. That takes basically 2 lines. But yeah. Oh yes, it's an inequality. Sorry, this is an inequality. But then you can immediately show that 1 over n to the half plus any epsilon positive, this converges to 0 almost surely even, as n goes to infinity for any bounded function f epsilon. Okay, so, and also again, this holds very generally for general determinable point processes where the projection operator is the kernel and where you have endpoints. Right, so in particular, it means that if I take epsilon as a half, which is much larger than the optimal one, of course, but then I know that if this expectation value has a limit, then I also know that this actually we have almost sure convergence. Okay, so you get almost sure convergence for free, even for bounded functions. So this is, I think this is quite a strong statement. Okay, and again, this holds always. There's no conditions on the measure mu yet. Okay, but of course we wanted to analyze the fluctuations, and we hope that the fluctuations are of order 1. So this is much stronger than we have here. So we need something extra, and this is also where we need to see one of that the function is differentiable, and we will show that actually that has been shown before that if you have a C1 function, the variance can be bounded in a much better way. Right? I should also say that this bound here is actually, we believe, is close to optimal. In the sense that if you would take a continuous function, then this is as good as it gets. You can construct some strange examples for which an improvement of this bound would fail. Okay, so but for differentiable functions, you can do much better. Okay, so this is what we're going to do. So now, okay, let's compute this variance of the linear statistic for a differentiable functions. But first, let me rewrite the variance a little bit. Well, I start with the fact that for a determinable point process, you can always write the variance as a difference of 2 integrals. We have a single integral here of fx squared times the diagonal, and then fx times fy times the square of the kernel. Here I also used actually the kernel symmetric. Then using the reproducing property, I can make this into a symmetric form. Okay, and this is just nicer because I can turn the first integral into a double integral because by the reproducing property. Okay, well then I'll do a simple identity. I just divide by x minus y, and then I multiply by x minus y here. Okay, so this is my, then I use the fact that I have a Christoffel-Darboux formula for the kernel. Right, so now I use the special property that I'm with an orthogonal polynomial ensemble. I can write this as the polynomials, this Christoffel in terms of the polynomials n and n minus 1, and the recurrence coefficient in front. Okay, so this is a nice way. This is a form that we will use in 2 ways now. So first of all, suppose now that we have a function that is Lipschitz with a Lipschitz constant fl. Then I have this variance. I just copied this from the last line from the last slide. I just estimate this term here, which gives me the Lipschitz constant here, and then this double integral over the polynomials. But I can square this, use the orthonormality actually, and this gives me just the Lipschitz constant squared times a and n. Okay, so this means that if we have that the recurrence coefficients a and n are bounded, then the variance remains bounded. And I should mention this is probably, maybe there's an earlier reference, but I've seen this exact computation by Pasteur in the paper in 2006. Okay, I don't know if there is a prequel to that, but it's a standard thing.
So is this where the one
No, no, no. This is general. No, no, one cut is not important.
So then some of these ANs are zero.
Yes. No, no, no. If you have multi-cut case, then you have periodic behavior in the recurrence coefficients. I will say a few words about this later. But it's not important right now. We're just trying to figure out if we have the right normalization. I should also say that the recurrence coefficients remain bounded. This is typically the case if you have a measure mu that is compactly supported, because then the recurrence coefficients are bounded by the norm, by the length of the interval, right, of the support. So this is not a strong requirement. So if we combine it with our concentration inequality, let's say that if f is Lipschitz, then and we know that the recurrence coefficients are bounded, then the fluctuations of order 1, and we actually have exponential tails uniformly in n. Okay, so that's the first. So we know we are on the right order, and so there is no regularity in the measure mu. Okay, so now let's do this computation again, but let's take a test function that is a polynomial. So if f is a polynomial, then you can actually rewrite it in a different way, because then the ratio here will be again a polynomial in degree in the variables x and y. It's a fixed polynomial, so I can use the recurrence to work this out. And what I get is that the variance can be written in terms of finitely many recurrence coefficients, an plus k and bn plus k. And the number of terms depends on the degree here. But actually, this brings us to an important point. Because if we have the Jacoby operator, so this statement says that the variance only depends on a very small part of this Jacoby operator, namely around the NN entry, I have a fixed window, and this window it only matters for this variance. So when n goes to infinity, I just take this window to infinity, and I have to see what the recurrence coefficients behave here, right? But this is only for the variance, so you could ask yourself, what about the higher moments, the higher cumulants? Okay, so this is the statement that I just said. What about the higher moments? But actually, it turns out they have the same principle. So and this brings me to the first general theorem, that if you assume that you have, if you take this box, you take the limit n to infinity, and for arbitrary size of the box, you have a limit, then there is a central limit theorem for the linear statistics. Okay, so we have xn of f minus exn of f converges to this normally distributed law, where you see this half Sobolev norm appearing here again. And the values a and b, they enter again in the rescaling of the function f. Okay? Now, you can do a little bit better. You don't even have to have that this converges along each n, for each n, but you can actually also have convergence along subsequence. The same principle applies. And we also have a theorem there that you can actually have central limit theorems along subsequences. Okay? And so then everything depends on the subsequence, of course. Okay? And I should say that these central limit theorems only depend on the polynomial of f, so the linear statistic is the moment of the empirical measure here. Right? But that also indicates that maybe we can construct some Jacoby operator where we have different limits along different subsequences, which means that we have different central limit theorems for the same model. Okay? So, okay, that was for polynomial test functions. So I promised I would go to C1 test functions. Well, of course, if you have it for polynomials, you can try to approximate a C1 function with polynomials, and that's how we prove it. And of course, if everything is already on a compact set, then you can just do this uniformly and everything works out, right? But we also want to include the unitary ensembles, and then we are working on an unbounded set. So then we need to get some condition, and the condition is the following. So we suppose that there is some compact set E for which the moments of the measure knxx d mu restricted to the set, to the complement of E, converge sufficiently fast to 0. Okay, and knxx is the mean density of points. So this is saying that the mean density of points lives essentially on a compact set. Okay? And then, if we have that, we can prove that the statement holds for any continuous, for any C1 function f with at most polynomial growth in infinity. Okay, and this is not optimal, of course. The optimal should be the half Sobolev norm, but it's quite optimal because we don't need C2, or maybe we saw some theorem yesterday also with C6. This is C1. Okay, we cannot get better than C1, but maybe with some extra work, I don't know. But we didn't manage to push it. So in particular, as I just said before, if we have a non-varying measure and just start with something with compact support, then it holds for any f immediately. Okay, now this condition, you may think, is this condition easy to check? Well, if you're, for example, in the Unitary Ensembles, you can prove that this diagonal of the kernel actually outside a compact set goes exponentially fast to 0. So there is little issues then there. Of course, it needs to be uniformly, but it's not a difficult condition to check. Okay, so examples. So the first examples that I want to give, you can do so you can take the unitary ensembles with some potential v, and if you have that, okay, and some of the general condition on v, if you're in the one cut case, then you can prove if you have a one cut, then you can prove that these recurrence coefficients have limits. Okay, it's not completely equivalent, but it's basically morally the same thing. If you have limits for the recurrence coefficients, we have one cut support, and vice versa. It's morally not completely true, but okay. You can prove this. And then, if we look at the lozenge tiling of the hexagon, well, then we have the Hahn polynomials. The Hahn polynomials are very explicit. So you have the recurrence coefficients, very explicit, closed form. You just compute what the limit is, and this gives you a CLT. Okay, so that's just, and you can do this with all kinds of, play this game with classical examples. So they follow once you have the recurrence coefficients in hand. So now you can ask, how general can this be? What kind of measures can we allow? And I want to mention a theorem by Denisov-Rachmanov that is a very general theorem that says that if you have a measure that is compactly supported, where the essential support is an interval, gamma delta, and the absolutely continuous part is positive, Lebesgue almost everywhere on that interval, then you have limits for the recurrence coefficients. So you have a limit, so you have a central limit theorem. Okay, so, and this is quite general because this shows also that we can allow for a singular part in the measure. Okay, so there is, even without regularity, I mean, for a very weak regularity in the measure, you have a CLT. So a third example is that we actually can construct some crazy examples. I mean, instead of starting with the measure, we can also start with the Jacoby operator and go to the measure. And we can use that to construct some interesting examples. So the first one is the following. We partition n into some blocks. So A1 should be B1, A2, B2, and so on. And we make sure that the length of AJ is 2 to the j squared, and the length of BJ is 3 to the j squared. Okay, so we have these blocks that increase in size significantly. I mean, quite rapidly, right? And then we set all the recurrence coefficients on the diagonal to 0, but we choose the recurrence coefficients an to be 1 if we are in the block AJ, and a half in the block BJ. Okay, so we have these large growing blocks where you only see a half, and you have these large growing blocks where you only see 1. Right? Then you can prove, it's a theorem that this is it's a singular continuous measure with respect to the back measure, singular measure with respect to the back measure, and it's supported on -2 to 2. Okay, and you can also prove that actually there's still a nice limit for the density of points. It converges to the equilibrium measure on -2 to 2, which also implies immediately we have almost sure convergence because of our concentration inequality before. But then we have 2 growing blocks, so we can take the middle of the center in the block where we have half, but we can also take it where we have all these ones. So we have 2 different types of central limit theorems. In one, the coefficients are given by this integral from 0 to 2 pi of f cosine theta, and in the other one we have this 2 cosine theta. which is a different central limit theorem. So although that there is it's still there was a limiting distribution of points to the equilibrium measure, you can have two different types of fluctuation theorems. So this is an interesting phenomenon that happens here. And you can play a little bit more. You can modify this example a little bit. I don't want to go into the details, but you can actually adjust it in such a way that you have a continuum of central limit theorems. So for each a between 1/2 and 1, so you fill in the gaps between the 1/2 and the 1, you can find that there are these limits as j goes to infinity, which means that we have a central limit theorem for each a between 1/2 and 1. And still in this case, we have that the limiting distribution of points is still going to the equilibrium measure. Okay, so these are some crazy examples that you can get. And so in the multicut case, the recurrence coefficients are polynomial. So they don't, periodic, right? The recurrence coefficients typically are periodic. And then sorry about that? Quasi-periodic, yes. Sorry, yes. No, because then there is no limit. No, because it cannot alternate, right? I mean, I said that the limit in these blocks has to be, basically the blocks have to be tuplets in the end, and not too periodic. First of all, we know there is no Gaussian limit. Yes, this is, for example, Shabina proved about the fluctuations for the partition functions, and they also have the quasi-periodic behavior there. You see it. So there is no central limit theorem there. But I will actually say something about it. So I will come to it. So, okay, so the next concept I want to speak about is right limits for Jacoby operators. So this is a notion for Jacoby operators, and I will formulate first the results that I just already had in terms of right limits, and then I'll show you maybe something about the multicut case. So okay, so we have the Jacoby operator here. I also need the Laurent operators and the Toeplitz operators. So the Toeplitz operators these are just semi-infinite matrices where we have that are constant along the diagonals. And the Laurent operator is semi-infinite, so it's infinite in both directions. Okay, and I will only use those matrix operators here with in a band structure. Sorry. So Q and P are given numbers. So these are the bands of the Toeplitz matrix. Right? And this S is called the symbol for the Toeplitz operator, the Laurent operator. Okay, so these are just constant along the diagonals, and along each diagonal we find one of the coefficients in the polynomial. Okay, so using that definition, I can just say that, well, if in my previous theorem, right, okay, so I need one more definition. Then a two-sided infinite matrix JR is called a right limit of Jn n if we have the following. So we take this block and we set n to infinity, and if there is a limit, then we call that the right limit. Okay, and this limit, we only need a limit along a subsequence. Okay, so one Jacoby operator can have different right limits. Okay? So if you think about it in the results I had so far, we can say these are when these right limits are actually the Laurent operators. Okay, these right limits are two-sided infinite matrices, and these will right. Okay, and then if these limits, if the recurrence coefficients need to have limit, then the right limit is a Laurent operator. Okay, and these right limits have been used. They are introduced by Last and Simon, and have been used to actually, let's say, to characterize spectra of Jacoby operators. I don't want to go into detail there, but they have been proved useful. Okay, so what we actually prove, this is just a repeat of the theorem that I had before. Suppose that LS is a right limit of the Jacoby operator, then you can prove that that we have a central limit theorem where the coefficients are not. I rewrote the definition of the coefficient here slightly. So we have an integral in the complex plane, contour integral, where we have f of s of z, where s is the symbol of the matrix. Okay, so this is just restating the previous theorem.
But you're confusing that because isn't the periodic case that you have a right limit there?
Yes.
Along the right kind of subsequence?
Yes, yeah, but then the right limit is not Laurent.
Oh, sorry. What is Laurent?
Laurent. So Laurent means we have this
Just to
as a constant diagonals. We have constant diagonals. Right. So this is okay. But now comes the next theorem. We actually have a fluctuation result for any right limit. So given any right limit, doesn't have to be Laurent, but just anything, or maybe two periodic. So here, the recurrence coefficient is quasi-periodic, but then the right limit actually becomes okay. But so here, if we have a right limit, so any right limit for subsequence nj, then I have a limit theorem for the fluctuations, although it's no longer Gaussian. It's given in terms of this difficult determinant, and to understand the determinant, so I'll introduce some notation. So the JMR, this is cutting off JR, taking a 2m by 2m block around the center. And then we have P minus is just a projection on the negative coefficients. And then you can view this as an operator on L2 of z. And then you have to compute the limit of that operator here. Okay? Well, this is, of course, a difficult thing to compute. And we can only compute it if this JR is tuplets, or Laurent, sorry, Laurent. But it would be nice to actually be able to compute this in some other cases, periodic cases. Right? So, but one thing is interesting about this theorem is that we have that for any right limit, there is a limit theorem. Right? So all the possible central limits that you would get sort of characterized by all these right limits of the Jacoby operator. Right? Okay, so we can prove that the limit exists. These are two limits, they both exist and they're equal to each other. But it's difficult to compute this in general cases. Right? So we want to that if you want to, that is something we've been trying, but we have not been very successful, is to get sort of multi-case fluctuations to retrieve the results by doing these, by computing these determinants for other right limits. Okay, but we have not been so successful yet. Okay, so that closes the discussion on the orthogonal polynomial ensembles. So now I want to say a few things about biorthogonal ensembles. So a biorthogonal ensemble is the concept of the name biorthogonal ensembles was introduced by Borodin some time ago, but they appeared before. But there's a general class of ensembles that also appear naturally in random matrix theory. So suppose we have two linearly independent two families of linearly independent functions, phi j and psi j. Then you can construct the probability measure on Rn proportional to this, right? And now, of course, I need positivity here, but I'll also assume this, right? So that this is a probability measure here. Okay, so we have the product of two determinants. You can get the orthogonal polynomials back again by taking phi and psi equal to a monomial. Okay, so we can assume without loss of generality that these families are biorthogonal to each other. So we have phi kx, psi lx is delta kl. Right? So this is why they're called biorthogonal ensembles. And also in this case, biorthogonal ensembles, they're also determinantal point processes on R here, where you have a formula for the kernel. Now you don't have a Christoffel-Darboux formula, but you still have this formula. Now the problem with this operator here is that it's still a sort of projection operator. You still have kn squared is k, but you don't have the symmetry anymore. And this complicates the concentration inequality, actually. So this, we would like to have some concentration for this kind of operators, but we haven't been able to get that. Okay, so now what we'll assume is that because we have everything, all the theorems were in terms of the recurrence, I mean the Jacoby operator, so the recurrence. So we will assume that there exists some banded matrix, banded matrix J, which is just the analog of the Jacoby operator, but we allow for more bands. Okay, so this is So this actually means that the phi's here have a recurrence. Okay, and we also allow that we have the varying case, so we allow the Jacoby operator J to depend on n. But if that's the case, if it depends on n, the number of bands remains fixed. Otherwise, the number of bands cannot grow. That would. This is okay. That's a good question. It is a natural assumption because there are many biorthogonal ensembles that admit such recurrence. Okay, in particular, if you have multiple orthogonal polynomial ensembles, then this is the case. Now, why these natural? Maybe I can just briefly say some examples. So so unitary ensembles with external source are examples of those. Okay, so maybe I can be a little brief here. So if you have a unitary ensemble with an external source, or equivalently, you look at non-intersecting paths with one source and several things, then this is an example. Okay, and so this is a biorthogonal ensemble. This is something that's well known. The fact that you have a recurrence follows by a result of Blecher and Kailas. They analyzed this using multiple orthogonal polynomials. You can show that this is a biorthogonal ensemble constructed out of multiple Hermite polynomials with m weights. What this is? M is the number of different eigenvalues. Yeah, so maybe I should spend a little bit more time here. So A is a diagonal matrix with eigenvalues A1 to AM. So we have m different eigenvalues, or m different endpoints, with multiplicities k1 to km. Okay, and then you can show that there's a concept of multiple Hermite polynomials, which is multiple orthogonality, and these polynomials they satisfy in m+2 recurrence. Okay, so this is an interesting model. So it's interesting to try to generalize things for biorthogonal systems with higher recurrence. Okay, I will not say. Another example comes from two-matrix model, right? So where you actually have the second matrix, A is not constant, but also is random. So you look at two matrices, M1 and an M2, that are taken randomly with respect to a measure of this form. Okay, and okay, then you can show, that was proved by Aina and Mehta, that there is biorthogonal polynomials. So these are characterized by this condition that also integrate this random matrix model. So we have a polynomial Pj of degree j and Qk of degree k that's such that we have this orthogonality here. It's not a Hermitian orthogonality, so you have to worry a little bit if it exists, but it does. But you also have these integrate this model. Yes, so that's so maybe I should say. So when I look at only the eigenvalues of one matrix M1, when I average over the second, then I get a biorthogonal ensemble where these functions phi j are constructed like this. And maybe just say that these polynomials Pj, they actually satisfy dw plus 1 recurrence, where d is the degree of w here. Phi and w are polynomials. Okay, so there is an interest in studying these biorthogonal ensembles with a higher band structure, a larger band structure. Okay. And I should also say that we actually, this model we have been working on the last few years quite a bit. And we can actually compute some asymptotics for this model. We can also compute the asymptotics of the recurrence coefficients, which are, of course, important for the next theorem, because we will express a central limit theorem in terms of its recurrence coefficients. Okay, so that comes here comes the theorem. Assume that the Laurent operator S, which now has this general form because P and Q, this is related to the number of terms in the recurrence. So if we have a Laurent operator, which is a right limit of this Jn now, which is not a Jacoby operator, but has larger bands, then we have a central limit theorem for polynomial f. Right? And now the coefficients are these type of integrals, but S is no longer a simple polynomial in z1 and 1 over z, but it has a different structure here. Okay, so this is how the difference between these bands comes in. Okay, so now note, since it's not symmetric, we don't have a concentration inequality, so we cannot extend this to f of C1. But I wouldn't be surprised that with an extra work, for example, in a two-matrix model or an external source model or in any other biorthogonal polynomial biorthogonal ensemble of interest, you could actually extend it using the same ideas. Actually, in a recent paper with Kurt Johansson, we needed a concentration of the quality of the similar type where we also had a kernel that was not symmetric. And with some work, we could still get the same concentration quality. Okay, and then we have the same theorem for for general right limits. So if you have a general right limit of this Jacoby operator, you still have the same theorem, only for polynomial f, of course. Okay, so that concludes. So that concludes the biorthogonal polynomial ensemble.
No,
So
can I go
sure.
back to the two-matrix model? So what
Yeah.
what is specifically the result that you get with the two-matrix model?
Which result?
That's what I was trying to find out.
So it's just for the purpose of an example, I just want to know that there is a dw plus 1 recurrence. So it's an example. The model is an example of the case of the
But
general.
can you use those now? Can you use the information you get to say something about the two-matrix model?
Yes, yes.
What can you say?
So we can say, so we have been analyzing the recurrence coefficients here, right? So when we know how the limit is, we can do the asymptotic analysis.
What are you looking at the asymptotic analysis of? Not clear.
Oh, the asymptotic analysis of the polynomials. We do this with Riemann-Hilbert technique, so you can find everything for the polynomials what you want. So you can find the asymptotics of the Plancherel-Rotach for the polynomials. You can find the recurrence coefficients, limits of those, also of the kernel. We typically only have been computing the asymptotics of the kernel and the limiting distribution of the zeros, but you can also do the recurrence coefficients.
Is this a way of asymptotically evaluating the integral, or saying something about the eigen?
Of the polynomials, of these polynomials here, and for that reason also the eigenvalues of an M1. Yes. Okay. Okay, so yeah. Okay. Okay, and I should also say actually for this kind of biorthogonal ensembles, I don't think there's any central limit theorem so far here. So that's also something that is new here. Okay, so maybe I want to say a few words about the proof, and the proofs are not so very hard actually, but you need to use some tricks. So what we do is you use the cumulant expansion here. So we take the moment generating function for the linear statistic, and then we start writing, okay, this is a Fredholm determinant, but the determinant, by taking a log, I can make this into a trace, so we get the exponential of a trace of the log. Then I do an expansion of this operator that I have here in small t. Okay, so and I write this for small t, and I organize all the terms, and then I get these coefficients here. And okay, these are very ugly, but this is what they are, right? So we have a double sum from j is 1 to m minus 1 to the j over j times this big sum over L1 to Lj that sum up to m, and you get these traces here. Okay, it's horrible to see, but okay, that's what it is. Right? So now you might ask, okay, what we need to do for central limit theorem is to have to prove that the second one converges to the variance with a factor 2, and the rest converges to 0. Right? Just proving the cumulants to 0. Now there is immediately a problem, because if you start working on this, one way of trying to prove that the cumulants go to 0 is to prove that these terms here, these traces go to 0, but they don't. There's no reason for them to do. In fact, actually they grow linearly with n. So this is a problem, and you need to do it. So a central limit theorem is actually essentially the result of a very subtle cancellation here, right? Because you have these terms growing linearly with n, and then you have this minus 1 to the j. So that's what you need to capture. Right? So the first trick we did is to say that if you take, okay, so here you have this ugly sum here, and then you have this trace of this operator. If you set this operator to 1, then you get a nice identity, because if you just set it to 1, then this is 0. And this simply comes from, the proof of this is just writing x in a difficult way and then do an expansion of x as we did before. Okay, that's very simple. Okay, but and this is a standard identity that has been used before also. So, but then you can just plug it in, and I can take instead of I rewrite my cumulant here in terms of the trace of this product, and I just subtract the trace of f to the m, kn. Note that L1 to Lj, they add up to m. Okay? So this is how we rewrite it. And now we can prove that each term in this sum is actually does not grow any more linearly with m. Right? So that remains nicely bounded. Right? And how do you see that? Well, okay, you got the difference of the two traces. Well, if they would commute, right, I can bring all these f's in front, and then the kn, all the kn to the right. I use that the kn squared is kn, so then I see that these are the same. Right? So if they commute, it's clear. But they don't commute, of course. So if they don't, but then the best thing you can do here is to find this estimate here. So you estimate the difference between the traces of j times m squared times the subnorm of f times the Hilbert-Schmidt norm of the commutator of f and kn. Okay? Sorry, what? You get 2 actually because you have the square, right? The other ones you just the other ones you just estimate kn with the operator norm, and the operator norm is 1 because it's a projection. So you throw them out. Okay. And then you use an identity that I wrote actually down. If you realize what this Hilbert-Schmidt norm means in terms of the operators, that's actually an identity I already wrote down in some slides before. This is exactly the variance. So the variance is the Hilbert-Schmidt norm of the commutator. It's a nice formula actually. So now you can estimate all these cumulants in terms of the variance only, and this gives you the concentration inequality that we had before. Okay, and this is what we do, and so this is what we do to get the concentration inequality. But it's not sufficient yet, because we want to go to the central limit theorem, and with the central limit theorem, we just need to set some extra steps. Okay, so in the central limit theorem, I have not used, so note actually, I haven't used anything on the kernel other than the fact that it's an orthogonal projection. So this is why the statement actually, concentration inequality is general. So now let's use the fact that we have the orthogonal polynomials. Okay, so then I write each trace here as the trace of fj. I just realized that this f was a multiplication operator, multiplication by x, that's what j is. Right, so I have an f is a polynomial, so I have this fj to the L1, and kn is just projecting on the first coefficients, pn. Okay, you just use the orthogonality to write this in this way. Okay, well, this doesn't help you much to prove that it's small, but it helps you in some sense. Because the j is a banded matrix, the f of j is banded, and if you then look at the difference between those traces, then you will see that all these differences, they only depend on a very small part of the Jacoby operator. They only depend on these small corners in these boxes here. Okay, and that comes from the band structure of J. Okay, you need to. This is a little combinatorial argument, but it's not difficult to prove actually. Once you know what to prove, it's not hard. You can show that. Okay, so this does not prove any asymptotic behavior, but it does prove something. It only depends on this, on this box. So this leads to the comparison or some universality principle. If J1 and J2 have the same values in this box in the limit, then the fluctuations should be the same. All right, so we prove actually universality for the fluctuations. Right? As long as the right limits are the same along the same subsequence, the fluctuations are the same. Which means that if I have, for example, a Laurent matrix as a right limit, I only have to check any matrix that has the Laurent matrix as a right limit. And there is a special one, the Toeplitz matrix, as of course the one as a right limit, because if I shift Toeplitz matrix, I just get the Laurent matrix. Okay. Okay, so how do you do this for the Toeplitz matrix and also for S of z? So for the concentration inequality, actually, I need this to be symmetric, but this actually also holds for the biorthogonal case. Right? So now we need to prove a lemma, a theorem, on Toeplitz operators, and banded Toeplitz operators here, actually. We need to prove that this Fredholm determinant, which is the moment-generating function of the linear statistic, in case the J is a Toeplitz operator, and we prove that this is the exponential of half times the h half norm. Okay, and okay, we prove this, and this is actually the proof that we have is very similar to a strong sacred limit theorem. So we first thought that this must be known in the literature. We checked with Harold Whittam, and he said, well, you should ask Thorsten Erhard, and we asked him, and he said also it's not known. Although the proof is almost identical there. It's very similar. You use the tricks that are quite similar. Okay? But then you can prove the statement. And I just wanted to mention that in that proof, you use Erhard's generalization of the Helton-Howe-Pincus formula that says that if A, B is trace class, then you have the determinant of this product of these exponentials is e to the half times the trace of AB. And this is where the final cancellations actually take place. This is a beautiful formula that actually captures in the end. This is actually why the central limit theorem comes true in the end. Okay, that's all I wanted to say. Yeah.